Hello, everyone, and welcome to this explainer. Today, we are mastering C arrays. We're going to take a deep dive into some fundamental programming techniques that literally every software engineer needs in their toolkit. We'll look at how to protect your data from accidental changes, how to organize a bunch of chaotic data using a classic algorithm, and finally, we're going to pull the whole shebang together by writing a program to analyze a real-world statistical case study. It's going to be fun, so let's get right into it.
Okay, let's dive into this. Here is our roadmap. We're going to quickly cover protecting arrays, break down the bubble sort algorithm, apply what we've learned to a survey analysis case study, visualize that data with histograms, and then finish up with a recap to lock in those key takeaways.
Section 1. Protecting arrays with const.
So here's the thing. When you pass an array to a function in C, you are basically handing over the keys to the castle. You're giving that function direct, unfiltered access to the original data in memory. But what if we want a function to only read the data, like just look at it and not change it? How do we prevent a simple, silly typo from accidentally corrupting our entire array? Well, this brings us to a really absolutely crucial software engineering concept, the principle of least privilege. This principle dictates that a function should not be given the capability to modify an array in the caller unless it is absolutely necessary. In C, we enforce this rule by using the const type qualifier in our function parameter definitions. By labeling an array as const, we are explicitly telling the compiler to lock it down. No unauthorized changes allowed. And this perfectly illustrates what happens when you try to break that rule. In the try to modify array function here, the programmer is trying to assign the value 2 to the elements of the array on lines 21, 22, and 23. But because we use that const qualifier we just talked about, the compiler steps right in and stops the program from even compiling. It throws error C2166, L value specifies const object. Now, seeing an error might feel bad, but actually, this compiler error is exactly what we want. It perfectly protects our original array back in main from being accidentally overwritten.
Moving right along to Section 2, the bubble sort algorithm.
Sorting data into ascending or descending order is, hands down, one of the most important computing applications out there. I mean, think about banks or phone companies handling massive data sets. They need things sorted. The sorting scheme we're looking at today is perhaps the simplest one to wrap your head around, the bubble sort, which is also known as the sinking sort. The analogy is super simple. Think of the array as a column of water. During the sorting process, the smaller values gradually bubble their way upward to the top of the array, while the heavier, larger values sink to the bottom. It achieves this by making several passes through the array, comparing successive pairs of elements side by side. So let's look at the actual setup for the bubble sort using nested for loops. We've got an outer loop starting on line 24 that controls the number of passes we make, and an inner loop on line 27 that handles the actual comparisons per pass. Now, I do want to point out a crucial performance tip here. Often, the simplest algorithms perform really poorly. Their main virtue is just that they're easy to write, easy to test, and easy to debug. Bubble sort is the poster child for this. It is super easy to program, but as we'll see, it wends painfully slowly because every exchange only moves an element one single position closer to its final destination. So the crucial point is how the actual swapping happens inside that inner loop. If the element on the left is greater than the element on the right, we've got to swap them. To do this, we use a 3-step assignment process. It's kind of like a shell game. First, we park the left element in a temporary variable called hold. Second, we overwrite that left element with the right element. And third, we take the original value waiting in hold and drop it into the right element. We absolutely must use this extra hold variable. If we just said a of I equals a of I plus 1, the original value would be overwritten and just lost forever. Now let's think about how many passes this whole bubbling process actually takes. If we have a 10-element array, we only need 9 passes to sort it. Why? Well, on the very first pass, the absolute largest value is guaranteed to sink all the way down to the bottom element. On the second pass, the second largest value sinks to its correct spot. By the time we finish the 9th pass, the 9th largest value has sunk into place, which naturally leaves the single smallest value sitting in the very first position. So the golden rule here is n-1 passes are all that's needed for an array of size n. And boom, here is the result. Notice how our original completely unsorted array is successfully transformed into perfect ascending order. The nested loops and that 3-step swap worked exactly as intended. But again, just a quick reminder, while this is a fantastic learning tool, sorting large arrays with this specific method is incredibly slow. Real-world applications handling massive data sets use much more complex, highly optimized algorithms.
Section 3. Case Study Survey Analysis.
All right. Computers frequently compile and analyze survey results and opinion polls, right? We are going to review a program that does exactly that, putting the array manipulation and sorting techniques we just learned to work. Our program is going to compute three fundamental statistical metrics from our raw data: the mean, which is just the standard arithmetic average of all the values; the median, which is the middle value, but only when the data is sorted; and the mode, which is simply the most frequently occurring value in the dataset. Now, what's really interesting about this setup is our raw data. We initialize an array called response with 99 actual survey responses. Each response is a rating from 1 to 9. We define a constant size of 99. This array right here represents the raw, chaotic data that we need to make sense of using our statistical functions. Let's process it, starting with the mean and median. To find the mean, we just total up all 99 elements and divide by 99, which gives us an average of 6.8788. Simple enough. But for the median, remember, order matters. Notice over on line 68, we absolutely must call our bubble sort function first before we can find the middle value. Once it's neatly sorted, we just pick the middle element by looking at the answer index size divided by 2. For our specific run, the median turns out to be 7. Now, a quick detail to keep in mind, our program logic here assumes an odd number of elements. If the number of elements were even, the median should technically be calculated as the mean of the two middle elements. Our specific function doesn't provide that capability just yet, but it's good to know. Section 4, histograms and load. Okay, for the last part of our analysis, we need to figure out which rating from 1 to 9 was given the most often by our survey respondents, and we want to visualize that distribution clearly. To find the mode, the most frequent rating, we count how many times each rating occurs and store it in a frequency array. Inside the loop starting on line 112, we actively track the mode value and the largest frequency. If the current frequency we are looking at is greater than our tracked largest, we update both of those variables. Then, for the really cool visual part, the inner loop starting on line 118 prints asterisks to represent that frequency value, building a clear histogram. When we look at the program's output, the longest bar of asterisks is for the rating 8, which occurred 27 times, so our mode is firmly 8. Section 5, recap and key takeaways. Wow, we've covered a lot of ground today, from basic memory safety all the way to algorithms and statistics. Let's bring it all together. Here is your quick checklist of core rules and programming patterns you definitely want to remember for your exams and assignments. First up, the const qualifier. Use it to enforce the principle of least privilege and prevent accidental array modification. If you try to change a const array, the compiler will save you with an error, like C2166. Second, bubble sort passes. Remember that sorting an array of size n requires exactly n-1 passes. Third, array element swapping. Always use a temporary hold variable. You cannot swap elements safely with just 2 assignments. And finally, median calculation. Your data must be sorted before you even attempt to find the middle value. And that brings us to the end of our explainer, but I do want to leave you with a final thought to chew on. We saw today that bubble sort is super easy to write, but it runs painfully slowly because those elements only move one position at a time. If you are working for a major tech company handling millions or even billions of data points, how might you sort those massive data sets faster? There are some incredibly clever, highly efficient algorithms out there waiting to be explored. So keep questioning, keep learning, and thank you so much for joining me to master C arrays today.